Let's start. I will start recording now. Good morning, everybody. This is the seminar cycle for the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk, the miniJPAS survey, the galaxy population in the miniJPAS cluster, mJPC2470-1771. And will be given by Julio Rodriguez. Julio is starting the third year of his PhD here at the Instituto de Astrofísica Andalucía in Granada. He started physics at the University of Granada from 2014 until 2018. And then he studied the master degree in physics and mathematics with the specialty in astronomy and astrophysics. He had already worked at IAA in the summer 2014 with Dr. Matilde Fernandez performing calibrations on a set of stellar spectra. And he now has come back, currently developing his PhD in the group of galaxy evolution as part of the JPAS collaboration, focusing on the effects on the environment in galaxy evolution. So thank you very much, Julio, for this talk. And please, the floor is yours.
Thank you very much, Rene. And thank you, everybody, for coming here today to my talk. I hope you're having a great day and a great week. So I'm going to talk to you about the current work that our group is doing in the largest cluster detected with miniJPAS, which is the mJPC2470-1771 cluster, or simply the cluster for friends. And since our group is the group of galaxy evolution, it's focused on the galaxy populations and the stellar population properties and of this cluster and how it can serve to galaxy evolution studies. So since it has been a long time since very likely since the last time you heard about JPAS, I'm going to give you a very brief introduction about what is this survey and why it is so powerful and why it is so interesting. JPAS stands for Javalambre Physics of the Accelerating Universe Survey, and it's been taking and will soon start to scan thousands of square degrees in the sky. And the target is to scan more than 8,000 square degrees, which is a very nice amount of sky. And the observations will take place in the Observatorio Astrofísico de Javalambre, which is ideal for this kind of surveys due to its location. And they will use the JST-T250 telescope, which is a telescope of 2.5 meters of diameter, and the JPAS cam in order to achieve to retrieve the data. The achieved field of goal with these two instruments is a very big one. It's 4.2 square degrees, which will, and as you can see in this image, courtesy of the JPAS collaboration, which is the first technical light of JPAS, the JPAS cam managed to observe the whole Andromeda galaxy in one single pointing. It will use 14 CCDs with a resolution of 0.2267 arcseconds per pixel. And so it will provide also specially resolved data for galaxies that are close enough. But most likely the great power of JPAS comes from its filter system, because it uses 56 narrowband photometric filters, which have a full width of maximum of 145 angstroms, with space by 100 angstroms each one, covering the whole optical spectral range. And it achieves a very resolution of 60, which is comparable to a very low resolution spectroscopy. So we have two factors, which is the large field of view without losing too much spectral resolution. In the meantime, we have the data from miniJPAS, which is a survey of 1 square degree along the AEGIs strip using the JPAS filter system and the Pathfinder camera, which has a smaller field of view. But with just 4 pointings, we achieved this 1 degree, and we already have a lot of data available to prove and to test what we can do with JPAS. It's also publicly available if you want to access it through the web page of the collaboration. And you can see that the observed region has also been studied in other surveys such as Javalambre or Othello. And here you can see how the night sky looks from the eyes of miniJPAS. Okay, so having this large field of view, it's a very powerful tool to develop studies about the environment. Here you can see a figure from the work from Maduri et al., which is in preparation yet, which is a slide of the overdensities of observed with miniJPAS at redshift 0.24. And here you can see how we have very useful data in order to see these overdensities and to study the environments of galaxies. And it's also very useful for galaxy evolution. There's already a work published by González Delgado et al., our group, showing how this data can be used for galaxy evolution studies. I choose here a figure where you can see the evolution with the redshift of the red and blue galaxies and the properties such as the stellar mass or the age, the intrinsic color, or the metallicity. Okay, so why are we so interested in the environment? When in denser environments, and when I mean denser environments, I mean galaxies that are near other galaxies that are not isolated, these galaxies start interacting among them, and this affects their morphology, their properties, the star formation, and there are several processes that take place, such as the run pressure stripping, the raisement, the cannibalism, merging and fusion, the tidal forces. And this is very interesting for galaxy evolution. Some results that I can talk to you about to give you a little bit of context. For example, the work from Dressler 1980, which found that as the density rose, so did the fraction of elliptical and SO galaxies. In consequence, the fraction of irregular and spiral galaxies decreases. In Dressler et al. In 1985, also found that they've less emission line galaxies in the cluster, which are denser environments. Kaufman et al. In 1984 found that the density strongly affects the stellar mass distribution. And in this figure, you can see that the fraction of the mass in the stellar mass in the local universe, and each color represents a density being. The cyan is the lowest density one, and then goes from cyan, blue, green, black, and red. And for example, the 4000 break, which is a very important indicator for stellar population, you can see a clear difference between less dense environments and denser environments. In the same year, Balog et al. Found a very result that is being used a lot by us, and is that the fraction of our galaxies increases with the density. But we can also talk about the Butler-Omler effect, which was first announced in 1978, which found that as the redshift increased, the fraction of blue galaxies in the core of clusters also increased. To name a more recent study, Peng et al. In 2010 found that the star formation rate of galaxies was independent of the environment at a given mass, which is what this figure represents. You have the mass and the star formation does change, but if you pick a fixed path and you start to use to look at the density, the star formation does barely change. Okay, so how are we going to use to study these densities, and how are we going to detect these clusters and groups? Well, we have a code which is AMICO, which stands for Adaptive Match Identifier of Cluster Objects, which is the one that is being used in miniJPAS to detect the groups and clusters. It is based on the optical filtering technique, which uses a noise in a template to try to reproduce the signal, and it uses several inputs such as the distance of galaxies to what we consider the center of the density and the brightness of the galaxies, etc. And it also provides an association probability for each galaxy to each group. If the group is very far off, of course, the probability is 0. But we can also use this probability for our studies, and we do indeed. And we use this probability as a criteria to select the members of the cluster that I'm going to talk about. And another thing that must be said about AMICO is that it also works very well for low mass groups, and there's also work in preparation about the stellar population properties of all the groups detected with AMICO. Okay, so let's talk about the data, because I've talked to you about the filter system, and so now I'm going to show you how the data, or how a galaxy looks from the eyes of JPAS. And these are 6 examples of 6 galaxies belonging to our cluster. The 3 upper ones are red galaxies, and the 3 bottom ones are blue galaxies. As you can see, just using the photospectra, you can see some difference. For example, in the 4000 break, it's appreciable that it's different for red and blue galaxies. And another very interesting thing is that thanks to having so many narrowband filters and so close, JPAS allows us to detect emission lines. For example, you can see here H alpha, oxygen 3, oxygen 2, as these peaks, as these filters that are brighter than their neighbors, not only brighter than their neighbors. And this is very nice, but in order to perform our studies, we do require a code to fit the spectral energy distribution of these galaxies. So that's why we use BaySeaGal, which is a code that has been developed by the Amorim et al. The paper is still in preparation, but as I mentioned, the work by Gonzalo Delgado et al. Already used it and proved how effective and how well it works. It is a parametric set-fitting code which uses Bayesian statistics and a Markov chain Monte Carlo approach in order to find the best fitting for the stellar continuum, which are the black dots that you see here. The colored dots are the observed magnitudes, and the black dots are the fitted ones. And since it must assume a star formation history parameter for this work, we are assuming a tau delay model, which is this equation that you're seeing here. And it depends on 2 parameters, and t sub 0, which is the look-back time on when the star formation began. T is in look-back time, the larger it is, the further away is in time. And tau, which represents how extended in time this how extended or how wide this exponential is. Since it is a Bayesian code, we can marginalize the parameters that we are interested in, and BaySeaGal provides the stellar mass, the metallicity, the extinction, and t sub 0 and tau. And we are also able to calculate the stellar ages through these parameters. As I mentioned, let me insist once more, given this large field of view that JPAS has, we can retrieve a lot of data from a lot of galaxies, and even spatially resolved, if if we want to perform such kind of studies. And due to its filter system, we can perform these fits of the stellar continuum and retrieve these properties, which is what we require for the galaxy evolutions. And for example, and here's another example from the work from González Delgado et al., and where you can see the mass with H as a function of the stellar mass, and in color code the different properties of these stellar populations. For example, the metallicity, the extinction, the rest frame color. So it's a very powerful tool. So, but let's go into what we are interested in, which is the cluster. Here you can see a photograph of the cluster as seen by miniJPAS, and there you can see the six same galaxies that I show you the spectra, 3 blue galaxies and 3 red galaxies. In particular, this is the BCG, which stands for brightest cluster galaxy. And we're going to consider that this is the center of the cluster. We have another image here, which is as I mentioned, the probability, the association probability given by AMICO to each cluster member. And here you can see the BCG. And this is the R200 radius, which is the distance at which the density, the mass density is 200 times the density of the universe at the cluster redshift. And the most notable things are two, is that the galaxies with greater probability are the ones closer to the BCG, and that the observations are incomplete due to the limit of the observations, the limit of the field of view. And so the clusters, we know that we are very likely missing galaxies over here, but we do still manage to find very nice results with this data. Here are the histograms for the stellar population properties. You can see the mass, the extinction, the metallicity, the red frame color, the H, and tau divided by T sub 0, which represents how extended in time was the star formation compared to how long it took place. Very low values indicate that the star formation stopped a long time ago, and higher values indicate that the star formation stopped or not so long ago, or that maybe it's even taking place today. We use two photometries in this work, which are the PSF core photometry, which has a smaller aperture, and it has a better signal to noise, and the outer photometry, which has a larger aperture, and it includes outer regions of the galaxies. And as you can see, the results do not change that much. The most noticeable thing is that mass is a little bit higher for auto, and its galaxies are a little bit bluer for auto too, due to this inclusion of the outer regions. But the most interesting thing that we can do with this plot is to compare them with the results of the whole AEGIs populations. And what we find is that the mass is more concentrated in the range of 10 to the 10 and 10 to the 11 solar masses. And the AEGIs are more or less within this range. But the most important thing to note is that we have a much higher fraction of red galaxies in this cluster when compared to the whole AEGIs field. In fact, this can be proved, this can be checked with the mass color diagrams here, which in the top panels you see the red frame color, and in the bottom panels you see the intrinsic color, and we use the color on the color code to mark stellar population properties. And the size of the dots are proportional to their probability. And along this work, that holds true unless I stated the contrary. And once we change from the rest frame color to the intrinsic color, correcting from extinction, we can apply the criteria developed by Diaz Garcia et al. To distinguish between red and blue galaxies, which is this line. Galaxies above it are stainedly red and galaxies below it are blue. As you can see, if you consider the extinction, these galaxies that will be in the valley when we correct from extinction move into the blue cloud. And the most notable thing is, and here is very clear that we have our overall density when we compare of red galaxies when we compare to the the population of the whole AEGIs field in this redshift being, which is the cluster redshift. But the distribution of the star properties remains the same. I mean, blue galaxies tend to be younger and to be more metallic, although the metallicity is more or less the same for all the galaxies, but the galaxies with the greater metallicity found here. And this is a very nice result, because the fraction of red galaxies, to give you a number, is 0.49 for us in this cluster compared to the 0.2 that is found in the AEGIs field at that redshift, which is almost the double. So this is telling us that the interaction is actually red in these galaxies. We can also study the spatial distribution of these properties. And the main idea that you have to keep is that the red galaxies are closest to the center, to the BCG, and they are more massive galaxies. They are older galaxies, and they are more metallic galaxies, although, as I said, the metallicity is more or less the same. And this gives an idea of how the cluster and the interaction forms. This is telling us that galaxies in the center, which is a more dense environment, and interact between themselves and tend to evolve more rapidly. We can also use this data to retrieve the mass density and the mean age. And we find these results, and this is the distance, the mass density as a function of the distance to the BCG, and we can see that it clearly decreases for both red and blue galaxies. And we find that the mean age is more or less the same for all red galaxies along the cluster, but there's a slight tendency to younger ages as you go away from the BCG. When I showed you the spectra, the J spectra, I told you that one very interesting thing is that we are able to see these emission lines. So the next logical step is to try to detect these emission line galaxies and study them separately. But we need a method to do this systematically and not just by looking a galaxy one by one. And establish and say, well, this looks like an emission galaxy, or this one not. So we established two methods. The first one is the median error method, which consists in looking at the filter that is closer to the H alpha emission, to the observed H alpha wavelength, considering the galaxy redshift. And we compute the median error of the observed magnitudes that are the closest of the 5 closest filter to H alpha. And we take a theta, which is a multiplicative constant, and this builds our threshold. And if the difference between the fit and the observed magnitude is greater than this threshold, then we consider it is an emission line galaxy. We set, this is manually tuned, and in order to achieve the best fit, we choose the theta to be 3 for red galaxies and 1 for blue galaxies. And this has a reason, and it's because blue galaxies tend to be much noisier than red galaxies. And if we chose the same value, the same threshold for both of them, we will either be losing a lot of blue emission line galaxies because the criteria is too strict for them, or we will be getting too many red galaxies that are classified as emission line galaxies, but in fact they are not, because their error is very small, and maybe it's just a small variation, and this threshold goes up, and they go over this threshold. And the other method is based in the artificial neural networks built by Martinez Light and Tal, by Ginés. And I think he will tell you more about them in November. So stay tuned if you want to know more about them. But the basic idea is what you have to know is that these neural networks are trained to calculate the equivalent width of several line emission lines, and we choose H alpha as a reference again. And what we do is that, following the work from Pascual et al. 2070, we choose this value, which is the equivalent width of the filter divided by the signal to noise of the filter -1, is the minimum equivalent width that can be measured by a photometric filter. So if our measurement of the equivalent width of H alpha plus its error, to consider the top of the error box, is greater than this minimum value, we consider that the galaxy is an emission line galaxy. We also impose that the measurement must be greater than its error in order to avoid galaxies that are just noise. So we have these two methods, and you can see here in this histogram of the intrinsic color distribution that they give very similar results. The median error is the cyan one, and the artificial networks is the green one. And they have a very similar distribution, but since our method is tuned in order looking for completeness rather than precision, than purity of the sample, we choose to keep just the intersection of both methods, which is this solid histogram. So we are more sure that these galaxies are in fact emission line galaxies. You can also see this distribution compared to the cluster, and the most important thing is that most of them are blue galaxies, which is what we will expect, because we're looking at H alpha. You can also see here the distribution of H alpha in the UI minus R, the color mass diagram and in the histogram. And you can see the most important thing to see is that the lowest values of the equivalent width are found in red galaxies, and blue galaxies take all the higher values of the equivalent width, which is what we will be expecting. But since we have red emission line galaxies, we have to consider the possibility of having active galactic nuclei in our galaxy, in our cluster. So we're going to try to determine the possible presence of them. And you can see here two examples of galaxies. This will be a very strong star-forming galaxy, which with its continuum very weak and with very strong emission lines. And this is the sample of this is an example of a Cipher 2 galaxy, which was also confirmed by spectroscopy with all the data. And what we use to distinguish between this are the one diagrams and the BPT diagrams. The one diagram was first designed by Steve Fernandez et al. In 2010. Well, the BPT diagram is a very common tool. So we're using 4 lines, 3 or 4 lines, depending on the criteria. If the galaxy is beyond it is at the left of the Kaufman 2003 transportation. We consider that this is a star-forming galaxy. If it's at the right of Cooley 2001, we know it's safer. If it is above the Cooley 2006 threshold for H alpha, if it's below, it could be a liner or it could be a retired galaxy. And in BPT diagram, we use the same criteria, but without these transpositions. So this is what the whole cluster looks in these diagrams. And as you can see, most of the galaxies are start forming. There are some galaxies that fall in this intermediate region, which are harder to classify. And if you look at the one we only will have one safer galaxy for sure, even though there are some more galaxies that could potentially be a safer galaxy. And the BPT diagram, it looks a little bit different, but in the case of that, we give more priority to the one diagram, since it only uses H alpha and nitrogen 2 to classify the galaxies rather than oxygen 3 and H beta. And this is because if there is no oxygen 3 emission, the measurement of the neural network cannot be trusted that much. So the results are that most of the emission line galaxies are most likely star-forming galaxies, about the 62%. About 20% being very, very, very generous could have a safer 2, but let me insist in the could, not in that they have. And the rest are liner galaxies or retired galaxies. Moving on, I have spoken about the star formation histories here. So we can also study these parameters in the cluster. So we focus in 4 parameters that come from 2, which is T0, as I mentioned, the greater the value of T0, the longest ago the star formation began. Tau divided by T sub 0, the smaller it is, the narrower the distribution is, or the narrower the star formation is. T max, which is the time, the look back time when the maximum of the star formation history was reached, and delta T sub q, which is the look back time when the star formation history decayed until the 10% of the maximum value. So what we are seeing is that T0 shows a very similar distribution for all the galaxies here, for red and blue galaxies. But if we divide the galaxies in the galaxies outside R200, this circle that we plotted before, and the galaxies inside, and the galaxies outside, what we find is that those galaxies with lower values of T0 are mainly blue galaxies located out of in the outskirts of the cluster. The same goes for the higher values of tau divided by T sub 0, which which will indicate that these galaxies have had wider star formation periods. And for the time where the maximum of the star formation was reached, in fact, as you can see, there are some negative values for this maximum, which means that these galaxies are yet to reach it, because we are talking in look-back time. Meanwhile, red galaxies are all located in these low values of tau divided by T sub 0, and in the low values and the high values of the T max. And in the end, the results for delta T sub q are more or less the same. Galaxies that took more time to reach that 10% point, or to that decreasement in the star formation history, are mainly blue galaxies aside the cluster, in the outer regions of the cluster. So this picture could be interpreted as a quenching, as a consequence of the quenching, since red galaxies are mainly in the core of the cluster, and we can see that they have evolved more rapidly. The star formation has already stopped. Meanwhile, blue galaxies are still forming stars, especially those that are in the outer regions, which are less dense regions, and they do not suffer so much the interaction and the gravitational potential of the cluster. We can also study the star formation rates, although we are using the specific star formation rate, which is the star formation rate divided by the star mass. And what we see is we study in first place the main sequence of the star formation. And since I remember what I mentioned before, the PSF core photometry uses a smaller aperture than the autophotometry. Usually, blue stars are located in the outer regions of galaxies, and this means that PSF core could be taking out these regions where massive new stars are being formed, and it could affect our studies on the star formation rates. So we choose to use both photometries and see the difference. And the color code we use is blue dots are the galaxies, blue galaxies that are both blue when we consider PSF core and the autophotometry. Same holds true for the red red dots and red galaxies. And galaxies that appear as red when we use the PSF core photometry, but change to blue when we use the autophotometry, and the same criteria as I mentioned before, that black dashed line, are the ones in gray, and we could name them transition galaxies. The galaxies with white dots are emission line galaxies, and the galaxies with a star inside them are galaxies with which their star formation in the last 20 mega years is under the 0.2% of the total mass. And this is a very interesting result because, as I mentioned, what you can see is if we use the PSF core, these galaxies that appear red are located here in the closest part to the main sequence of the star formation. But if we use the autophotometry, they do fit in this main sequence, although some of them are starting to exceed the main sequence. And a very nice check is that the galaxies with lower mass and highest specific star formation rate are actually emission line galaxies, which will be expected since H alpha is a tracer of the star formation rate. So these results could indicate that we are even able to detect transition galaxies using these two photometries. And last, I want to show you that the radial distribution of the mean specific star formation rate for blue, red, and transition galaxies using the PSF core and the autophotometry. This dashed line represents the criteria about Peng et al. In 2010. And galaxies above this line are considered to be star forming, and galaxies below this line are considered to be quiescent galaxies. So it is very interesting to see some things. The first one is that for red galaxies, the mean specific star formation rate remains more or less constant. For blue galaxies, the specific star formation rate tends to increase as we go away from the BCG, from the denser regions. And these transition galaxies do in fact change behavior when we change from PSF core to autophotometry. So in conclusion, we find that a larger fraction of red galaxies, in the cluster compared to the AEGIs field. We find that red more massive and older and more metallic galaxies are found closer to the BCG. We are able to detect emission line galaxies and active galactic nuclei. And our results are also compatible with a scenario where the red galaxies were quenched previously to the accretion to the cluster, and blue galaxies are in the process of quenching. And this is what I mentioned before. And the most important conclusion is that JPAS is a very powerful tool for the galaxy evolution and environment studies. So that's all I wanted to say, and thank you very much for your time.
Thank you very much, Julio. Now the talk is open for questions. Please raise your hand if you want to do a questions, and I will give you the voice. For doing that, please, in the bottom of the screen, you have a reaction button, then you can raise your hand there. So who will be the first in doing a question to Julio? Here we have one. Ignacio, please, go on.
Hi, Julio. Very nice results. So it's great to see JPAS, miniJPAS starting to work. I was wondering about two technical things. So in some cases, in some spectral energy distribution that you were showing, the scatter of the points were larger than the error bars with respect to the model that you were fitting. I was wondering which contribution to this scatter has issues or problem with the photometrical calibration of these filters of JPAS. So can you comment on that?
Well, I'm not the one who is in the most detail with the calibrations, but we do know that sometimes JPAS suffers effects from fringing, and it could be what is happening in some galaxies, especially red galaxies. I didn't stop there, but you can see here two red galaxies. One is in the Green Valley, but let me put this again. But this one has a very high equivalent width of H alpha, and it's in the red cloud. And this could be fringing effects. So the data in general is good, but yes, there could be some problems. But well, as I say, I'm not the one who's reading the data. I'm working.
My other question is related to the intrinsic galactic extinction correction that you're doing. Mm-hmm. Would you please comment a little bit more of what exactly you are doing, and also whether you make any correction considering the inclination of the galaxies, particularly the spiral ones?
Well, we are not considering inclination effects so far. We're working with the integrated whole galaxies. And so the answer is no, we're not taking that into account. And that's the matter of how the extinction works. This is how BaySeaGal works. It decomposes the spectra into an extinction, which is, a part that is dependent of the extinction, which is this one. The here is the extinction, and here's the spectra. Once we retrieve once we have the feed and we have retrieved all these properties, including the extinction, we go to our SSP, our single stellar population catalog. Well, it's not catalog, but our basis, and we use that to reconstruct the intrinsic spectra, and then we can reveal the rest frame spectra. And
so you assume an extinction low depending on the galaxy, or you just get the extinction internally?
Well, the goal is that BaySeaGal calculates the extinction that it requires in order to fit the spectra. It's in their calculation, tries to fit, say, the stellar mass, the metallicity, the extinction, and the star formation history in order to achieve the best fit to the spectra. So the extinction is part of the parameters that are being fitted to the spectra. And in order to correct extinction, we use all this information and we go to, I think we are using the virtual base, but I had to look at it to give you a share. But we go to our spectra basis and our stellar populations spectra basis, and that's how we reconstruct. And
okay. Thank you.
Yeah, thank you.
Thank you, Ignacio. Other questions for Julio? There is also no questions in the live stream. Maybe we can wait for another shy person that want to ask Julio. There is a good opportunity.
I don't bite anyone, most of, especially because the screen is behind me and I'm physically enabled.
Okay, seeing none. Thank you very much, Julio, for this nice talk. And I expect to see next week everybody here for the next seminar. Thank you, Julio.
Thank you, everybody.
Bye.
Hola.